Choosing an AI model can feel a little like choosing a vehicle. You might be excited by speed and features, but what really matters is whether it safely fits the roads you actually drive on. In this episode, we're going to get practical about selecting models securely, not by memorizing brand names, but by learning how to judge capability fit, understand predictable failure modes, and demand the right kind of transparency from the vendor. Beginners often assume the safest choice is the biggest model, the newest model, or the one with the most hype. But secure selection is a different mindset. Secure selection starts with being honest about the job you want the model to do, the mistakes it can make while doing that job, and the information you need in order to trust it in a real environment. By the end, you should be able to explain why model choice is a security decision, not just a performance decision, and you should have a clear mental checklist you can reuse without getting lost in marketing. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Capability fit is the idea that you select the smallest and simplest model that can reliably do the task you need, without bringing extra risk along for the ride. In security, extra capability can be a liability because it expands what the system could be tricked into doing or revealing. If your goal is to summarize meeting notes, you don't necessarily need a model that can write code, browse documents, and plan multi-step actions, because those abilities can create new ways for attackers to cause harm. The point is not that capable models are bad, but that capability should be intentional and justified. A good selection process begins with a clear task statement, like classify support tickets, extract key fields from text, or draft a policy paragraph for human review. When the task is crisp, you can evaluate models against it and avoid buying a rocket engine when a bicycle would have been safer and easier to control. To make capability fit real, you have to translate the task into requirements that matter for security, not just for accuracy. For example, do you need the model to handle confidential data, or can it operate on content that is already public? Does the model need to remember past conversations, or should each request be isolated so that nothing carries over? Do you need deterministic behavior, where you can reproduce results, or is some variability acceptable because a human will review everything? These questions drive the selection because they determine what kinds of protections you'll need later. A model that must touch sensitive data creates a larger privacy risk than one that operates on sanitized inputs, even if they appear equally accurate. Secure selection treats data sensitivity, memory behavior, and reproducibility as first-class requirements, not as details you bolt on after the purchase. A big misconception is that AI failures are rare, surprising events, like a system crash that only happens on a bad day. In reality, many model failures are normal, repeatable patterns that you should assume will happen. A model can confidently state something false, omit important context, misread a question, or follow a malicious instruction embedded inside the input. These are not edge cases. They are the kinds of failures that show up when a system is used at scale. Secure selection requires you to ask, when this model fails, what does failure look like, and how bad is it? If a summarization model occasionally produces a vague summary, that might be annoying but manageable. If a model used for access decisions occasionally fabricates a reason to approve a request, that becomes a serious security risk because it can directly enable unauthorized access. One important failure mode to understand is hallucination, which is when the model generates content that sounds plausible but isn't grounded in the input or reality. For beginners, it helps to think of the model as a powerful autocomplete system trained on patterns, not a database of verified facts. That means you should avoid selecting a model for tasks that require factual certainty unless you also plan for verification steps and constraints. Another failure mode is instruction following in the wrong place, where the model treats untrusted text as instructions, such as content from an email, a web page, or a document. This is closely related to prompt injection, where an attacker tries to smuggle instructions into the input so the model will ignore your intended rules. When you evaluate a model, you are not only asking can it follow instructions, but can it resist the wrong instructions when the environment is messy and adversarial. There is also a failure mode that looks polite on the surface but is dangerous underneath: oversharing. Models can reveal sensitive information that was present in the input, present in their context, or present in retrieved documents connected to the request. Sometimes this is obvious, like repeating a password that appears in a pasted log, but sometimes it is subtle, like leaking internal project names, customer identifiers, or security configurations that should not be repeated. If you are selecting a model that will ever see private data, you should evaluate how it handles redaction requests, how it responds when asked to reveal secrets, and whether it follows data handling instructions reliably. You should assume users will ask the system to show them things they should not see, either by accident or on purpose. Secure selection includes testing the model's tendency to comply, refuse, or guess when it lacks permission. Another failure mode is goal confusion, which happens when the model optimizes for being helpful rather than being correct or safe. A beginner-friendly way to think about this is to imagine a very eager assistant who would rather give you something than admit they don't know. In a security context, that eagerness can lead to risky behavior like inventing steps, making unjustified assumptions, or completing an unsafe request. This matters when selecting a model because different models and configurations behave differently under pressure, especially when the user is assertive or the prompt is ambiguous. You want a model that can tolerate uncertainty, ask for clarification when allowed, and decline requests when appropriate. If your use case cannot tolerate the model being creative, then creativity is not a feature, it is a risk factor. Capability fit also includes thinking about the model's interface and deployment style, because those choices change what kinds of failures become possible. A model that runs entirely within your environment has different risks than a model accessed through a hosted API, where data leaves your network. A model that supports tool use, where it can call external systems, has a bigger blast radius than one that only produces text. A model that keeps conversation history can create leakage across sessions if isolation is weak. Even if the core model is the same, these surrounding features change the security story dramatically. Secure selection is not just picking a model name. It is picking a model plus an operating mode, and the operating mode often drives the real risk. Now we move into vendor transparency, which is basically the difference between buying a tool with a clear manual versus buying a mystery box. Vendor transparency means the provider tells you what you need to know to assess risk, operate safely, and respond when something goes wrong. That includes documentation about data handling, retention, training use, and isolation between customers. It includes security claims that are specific, testable, and updated, rather than vague promises. It also includes clarity about model updates, because frequent silent changes can break your controls or change behavior without warning. For a secure program, you need to know whether your vendor can change the model behind the scenes, whether you can pin a version, and how quickly they communicate incidents. A helpful way to evaluate transparency is to ask what you would need during an incident. Imagine you discover that the model produced a sensitive output to the wrong user, or that a malicious prompt caused it to ignore instructions. In that moment, you need logs, timestamps, version information, and a clear explanation of what data is stored and where. You also need a support path that can answer security questions quickly and concretely. Vendors that cannot explain their own data flows or update processes create operational risk because you can't confidently contain or investigate problems. Secure selection prefers vendors that provide audit-friendly details, such as retention periods, deletion processes, and controls for isolating tenants. Even as a beginner, you can remember this principle. If you can't explain how it works, you can't secure it. Transparency also covers limitations, and a vendor's willingness to talk about limitations is actually a positive sign. A trustworthy vendor will describe known weaknesses, safe use cases, and cases they recommend against. They will provide guidance on how to configure safety features and what those features do and do not prevent. If a vendor claims their model is safe in all situations, or that it cannot be tricked, that is not a reassuring statement. It is a red flag. No model is perfect at resisting manipulation, and the secure posture is to assume attempts will happen and to design layers of defense. When selecting a model, you should value honesty about failure modes because it helps you plan controls realistically. Marketing that denies failure modes tends to push you into a false sense of security. Another dimension of transparency is how the vendor handles vulnerability reporting and fixes. Mature vendors have a clear process for reporting security issues, publishing advisories, and communicating mitigations. They may have programs that encourage responsible disclosure, and they may provide timelines for fixes and updates. You don't need to be a lawyer or a penetration tester to care about this, because the absence of a process means you might be the one discovering issues in production with no clear path to resolution. Secure selection includes asking whether you can obtain information about security incidents, whether you can receive notifications, and whether you can control rollout of updates. If a vendor can push changes without notice and without rollback options, that can turn a stable system into a surprise outage or a new exposure overnight. Model evaluation for selection should include simple but adversarial testing, because you want to see how the model behaves when users are messy, confused, or malicious. You can create test prompts that try to coax secrets, override rules, or produce disallowed content, and you can observe whether the model resists or complies. You can also test for reliability by giving the same prompt multiple times and checking whether the behavior stays consistent. Consistency matters because security controls often depend on predictable behavior. If the model sometimes follows your refusal rule and sometimes ignores it, you cannot confidently build policy around it. The goal of this testing is not to prove the model is perfect, but to learn its patterns so you can choose a model whose weaknesses are manageable for your specific use case. A secure selection process also looks at the cost of mistakes, which is a different question than the cost of usage. It's easy to focus on token cost, licensing cost, or hardware cost, but security cares about the cost of a bad output. If the model drafts an email and it contains a minor error, the cost might be embarrassment. If the model provides instructions for a dangerous action, the cost could be real harm. If the model leaks customer data, the cost could be legal, financial, and reputational. In practice, that means you might choose a less capable model for high-risk tasks if it is easier to constrain and less likely to wander. Or you might choose a more capable model only if you also implement stronger controls and stronger oversight. Secure selection is always a trade-off, but it should be an explicit trade-off you can explain. Finally, remember that model choice is not a one-time decision you set and forget. Models evolve, vendors change policies, and your own use case expands over time. The secure approach is to document why you chose the model, what assumptions you made, what failure modes you accepted, and what transparency signals you required. That documentation becomes your anchor when someone later says, "Can we add tool access? Can we connect it to sensitive data? Or can we switch to a cheaper provider?" When you have a written rationale, you can evaluate changes against it instead of making decisions based on urgency or excitement. Secure selection is the start of governance, because it creates a clear line between what the model is allowed to do and what it must never do. If you treat selection as a security decision from day one, the rest of your deployment and operations become far easier to control.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.